The Windscale fire of October 10, 1957 was the worst nuclear accident in Great Britain's history, ranked in severity at level 5 on the 7-point International Nuclear Event Scale. The fire took place in Unit 1 of the 2-pile Windscale facility on the northwest coast of England in Cumberland. The 2 piles had been built as part of the British atomic bomb project. Windscale Pile No. 1 was operational in October 1950, followed by Pile No. 2 in June 1951. The fire burned for 3 days and there was a release of radioactive contamination that spread across the UK and Europe. Of particular concern at the time was the radioactive isotope iodine-131, which may lead to cancer of the thyroid, and it has been estimated that the incident caused 240 additional cancer cases. No one was evacuated from the surrounding area, but there was a worry that milk might be dangerously contaminated. Milk from about 500 kilometers to of nearby countryside was diluted and destroyed for about a month. A 2010 study of workers directly involved in the cleanup found no significant long-term health effects from their involvement. Windscale piles. After the Second World War, the British government embarked on a program to build nuclear weapons. Skipping the lower-performance uranium-based weapons in favor of those based on plutonium, a plutonium breeding reactor system was designed to produce this material, which is not found in nature. The design was based on the graphite-moderated B reactor built at the Hanford site, which was known to British physicists who had been involved in the Manhattan Project during the war. The reactors were built in a short time near the village of Seascale, Cumberland. They were known as Windscale Pile 1 and Pile 2, housed in large concrete buildings a few hundred feet apart. The core of the reactors consisted of a large block of graphite with horizontal channels drilled through it for the fuel cartridges. Each cartridge consisted of a uranium rod about 30 centimeters long encased in an aluminium canister to protect it from the air, as uranium becomes highly reactive when hot and can catch fire. The cartridge was finned, allowing heat exchange with the environment to cool the fuel rods while they were in the reactor. Rods were pushed in the front of the core, the charge face, with new rods being added at a calculated rate. This pushed the other cartridges in the channel towards the rear of the reactor, eventually causing them to fall out the back, the discharge face, into a water-filled channel where they cooled and could be collected. The chain reaction in the core converted the uranium into a variety of isotopes, including some plutonium, which was separated from the other materials using chemical processing. As this plutonium was intended for weapons purposes, the burn-up of the fuel would have been kept low to reduce production of the heavier plutonium isotopes. The design initially called for the core to be cooled like the B reactor, which used a constant supply of water that poured through the channels in the graphite. There was considerable concern that such a system was subject to catastrophic failure in the event of a loss of coolant accident. This would cause the reactor to run out of control in seconds, potentially exploding. At Hanford, this possibility was dealt with by constructing a 30 miles escape road to evacuate the staff with this to occur, abandoning the site. Lacking any location where a 30-mile area could be abandoned if a similar event were to occur in the UK, the designers desired a passively safe cooling system. In place of water, they used air cooling driven by convection through a 400 feet tall chimney, which could create enough airflow to cool a reactor under normal operating conditions. The chimney was arranged so it pulled air through the channels in the core, cooling the fuel via fins on the cartridges. For additional cooling, huge fans were positioned in front of the core, which could greatly increase the airflow rate. During construction, Terence Price, one of the many physicists working on the project, began to consider what would happen if one of the fuel cartridges being pushed out the back of the core were to break open. This could happen, for example, if a new cartridge being inserted was pushed too hard, causing the one at the back of the channel to fall past the relatively narrow water channel and strike the floor behind it. In that event, the hot uranium could catch fire, with the fine uranium oxide dust being blown up the chimney to escape. When he raised the issue at a meeting and suggested that filters be added to the chimneys, the concern was dismissed as being too difficult to deal with and was not even recorded in the minutes. Sir John Cockcroft was alarmed enough to order that filters be installed, which required them to be constructed on the ground while the chimneys were still being built, and then winched into position at the top once the chimney's concrete had set. These became known as Cockcroft's Folly by workers and engineers. In the end, Price's concerns came to pass. So many cartridges missed the water channel that it became routine for staff to walk through the chimney ductwork with shovels and scoop the cartridges back into the water. On other occasions, fuel cartridges became stuck in the channels and burst open while still in the core. In spite of these precautions and the stack filters, Frank Leslie had discovered radioactivity around the site, but this information was kept secret, even from the staff at the station. Winner Energy. Once commissioned and settled into operations, Pile 2 experienced a mysterious rise in core temperature. Unlike the Americans and the Soviets, the British had little experience with the behavior of graphite when exposed to neutrons. Hungarian-American physicist Eugene Wigner had discovered that graphite, when bombarded by neutrons, suffers dislocations in its crystalline structure, causing a buildup of potential energy. This energy, if allowed to accumulate, could escape spontaneously in a powerful rush of heat. The sudden bursts of energy worried the operators, who turned to the only viable solution, heating the reactor core in a process known as annealing. When graphite is heated beyond 250 degrees Celsius it becomes plastic, and the Wigner dislocations can relax into their natural state. This process was gradual and caused a uniform release which spread throughout the core. Annealing succeeded in preventing the buildup of Wigner energy, but the monitoring equipment, the reactor itself and all of its ancillaries such as the cooling system were never designed for this process. Each annealing cycle was slightly different and progressively more difficult as time went on. Many of the later cycles had to be repeated, and higher temperatures were required to start the annealing process. Tritium production. Winston Churchill publicly committed the UK to building a hydrogen bomb, and gave the scientists a tight schedule in which to do so. This was then hastened after the US and USSR began working on a test ban and possible disarmament agreements which would begin to take effect in 1958. To meet this deadline there was no chance of building a new reactor to produce the required tritium, so the Windscale Pile 1 fuel loads were modified by adding enriched uranium and lithium magnesium, the latter of which would produce tritium during neutron bombardment. All of these materials were highly flammable, and a number of the Windscale staff raised the issue of the inherent dangers of the new fuel loads. These concerns were brushed aside. When their first H-bomb test failed, the decision was made to build a large fusion-boosted fission weapon instead. This required huge quantities of tritium, 5 times as much, and it had to be produced as rapidly as possible as the test deadlines approached. To boost the production rates, they used a trick that had been successful in increasing plutonium production in the past. By reducing the size of the cooling fins on the fuel cartridges, the fuel loads increased temperature, which caused a small but useful increase in neutron enrichment rates. This time they also took advantage of the smaller fins by building larger interiors in the cartridges, allowing more fuel in each one. These changes triggered further warnings from the technical staff, which were again brushed aside. Christopher Hinton, Windscale's director, left in frustration. After a first successful production run of tritium in Pile 1, the heat problem was presumed to be negligible and full-scale production began. But by raising the temperature of the reactor beyond the design specifications, the scientists had altered the normal distribution of heat in the core, causing hotspots to develop in Pile 1. These were not detected because the thermocouples used to measure the core temperatures were positioned based on the original heat distribution design, and were not measuring the parts of the reactor which became hottest. Accident. Ignition. On October 7, 1957, operators of Pile 1 noticed that the reactor was heating up more than normal, and a Wigner release was ordered. This had been carried out 8 times in the past, and it was known that the cycle would cause the entire reactor core to heat up evenly. During this attempt the temperatures anomalously began falling across the reactor core, except in channel 2053, whose temperature was rising. Concluding that 2053 was releasing energy but none of the others were, on the morning of October 8 the decision was made to try a second Wigner release. This attempt caused the temperature of the entire reactor to rise, indicating a successful release. Early in the morning of October 10 it was suspected that something unusual was going on. The temperature in the core was supposed to gradually fall as the release ended, but the monitoring equipment showed something more ambiguous, as one thermocouple indicated that core temperature was instead rising. As this process continued, the temperature continued to rise and eventually reached 400 degrees Celsius. In an effort to help cool the pile, the cooling fans were sped up and airflow was increased. Radiation detectors in the chimney then indicated a release, and it was assumed that a cartridge had burst. This was not a fatal problem, and had happened in the past. Unknown to the operators, the cartridge had not just burst, but caught fire, and this was the source of the anomalous heating in channel 2053, not a WNA release. Fire equals, speeding up the fans increased the airflow in the channel, fanning the flames. The fire spread to surrounding fuel channels, and soon the radioactivity in the chimney was rapidly increasing. A foreman, arriving for work, noticed smoke coming out of the chimney. The core temperature continued to rise, and the operators began to suspect the core was on fire. Operators tried to examine the pile with a remote scanner but it had jammed. Tom Hughes, second in command to the reactor manager, suggested examining the reactor personally, and so he and another operator went to the charge face of the reactor, clad in protective gear. A fuel channel inspection plug was taken out close to a thermocouple registering high temperatures, and it was then that the operators saw that the fuel was red hot. An inspection plug was taken out, said Tom Hughes in a later interview, and we saw, to our complete horror, 4 channels of fuel glowing bright cherry red. There was now no doubt that the reactor was on fire, and had been for almost 48 hours. Reactor manager Tom Tuohy donned full protective equipment and breathing apparatus and scaled the 80-foot ladder to the top of the reactor building, where he stood atop the reactor lid to examine the rear of the reactor, the discharge face. Here he reported a dull red luminescence visible, lighting up the void between the back of the reactor and the rear containment. Red-hot fuel cartridges were glowing in the fuel channels on the discharge face. He returned to the reactor upper containment several times throughout the incident, at the height of which a fierce conflagration was raging from the discharge face and playing on the back of the reinforced concrete containment, a Euroconcrete whose specifications required that it be kept below a certain temperature to prevent its collapse. Initial firefighting attempts operators were unsure what to do about the fire. First they tried to blow the flames out by running the fans at maximum speed, but this fed the flames. Tom Hughes and his colleague had already created a fire break by ejecting some undamaged fuel cartridges from around the blaze, and Tom Tuohy suggested trying to eject some from the heart of the fire by bludgeoning the melted cartridges through the reactor and into the cooling pond behind it with scaffolding poles. This proved impossible and the fuel rods refused to budge, no matter how much force was applied. The poles were withdrawn with their ends red hot. One returned dripping molten metal. Hughes knew this had to be molten irradiated uranium, causing serious radiation problems on the charge hoist itself. The exposed fuel channel was white hot, said Hughes' colleague on the charge hoist with him, it was just white hot. Nobody can believe how hot it could possibly be. Carbon dioxide Next, the operators tried to extinguish the fire using carbon dioxide. The new gas-cooled Calder Hall reactors on the site had just received a delivery of 25 tons of liquid carbon dioxide, and this was rigged up to the charge face of Windscale Pile 1, but there were problems getting it to the fire in useful quantities. The fire was so hot that it stripped the oxygen from what carbon dioxide could be applied. So we got this rigged up, Hughes recounted, and we had this poor little tube of carbon dioxide and I had absolutely no hope it was going to work. Use of water On the morning of Friday 11 October, when the fire was at its worst, 11 tons of uranium were ablaze. Temperatures were becoming extreme and the biological shield around the stricken reactor was now in severe danger of collapse. Faced with this crisis, Tuohy suggesting using water. This was risky, as molten metal oxidizes in contact with water, stripping oxygen from the water molecules and leaving free hydrogen, which could mix with incoming air and explode, tearing open the weakened containment. Faced with the lack of other options, the operators decided to go ahead with the plan. About a dozen fire hoses were hauled to the charge face of the reactor. Their nozzles were cut off and the lines themselves connected to scaffolding poles and fed into fuel channels about a meter above the heart of the fire. Tuohy once again hauled himself onto the reactor shielding and ordered the water to be turned on, listening carefully at the inspection holes for any sign of a hydrogen reaction as the pressure was increased. The water was unsuccessful in extinguishing the fire, requiring further measures to be taken. Tuohy then ordered everyone out of the reactor building except him and the fire chief in order to shut off all cooling and ventilating air entering the reactor. Tuohy then climbed up several times and reported watching the flames leaping from the discharge face slowly dying away. During one of the inspections, he found that the inspection plates Euro, which were removed with a metal hook to facilitate viewing of the discharge face of the Courier Euro, were stuck fast. This, he reported, was due to the fire trying to suck air in from wherever it could. I have no doubt it was even sucking air in through the chimney at this point to try and maintain itself, he remarked in an interview. Finally he managed to pull the inspection plate away and was greeted with the sight of the fire dying away. First the flames went, then the flames reduced and the glow began to die down, he described. I went up to check several times until I was satisfied that the fire was out. I did stand to one side, sort of hopefully, he went on to say, but if you're staring straight at the core of a shutdown reactor you're going to get quite a bit of radiation. Water was kept flowing through the pile for a further 24 hours until it was completely cold. The reactor tank itself has remained sealed since the accident and still contains about 15 tons of uranium fuel. It was thought that the remaining fuel could still reignite if disturbed, due to the presence of pyrophoric uranium hydride formed in the original water dousing. Subsequent research, conducted as part of the decommissioning process, has ruled out this possibility. The pile is not scheduled for final decommissioning until 2037. Aftermath radioactive release there was a release of radioactive material that spread across the UK and Europe. The fire released an estimated 740 terabecquerels of iodine-131, as well as 22 TBq of cesium-137 and 12,000 TBq of xenon-133, among other radionuclides. Later reworking of contamination data has shown national and international contamination may have been higher than previously estimated. For comparison, the 1986 Chernobyl explosion released approximately 1,760,000 TBq of iodine-131, 79,500 TBq cesium-137, 6,500,000 TBq xenon-133, 80,000 TBq strontium-90, and 6,100 TBq plutonium, along with about a dozen other radionuclides in large amounts. The 3 Mile Island accident in 1979 released 25 times more xenon-135 than Windscale, but much less iodine, cesium and strontium. Estimates by the Norwegian Institute of Air Research indicate that atmospheric releases of xenon-133 by the Fukushima Daiichi nuclear disaster were broadly similar to those released at Chernobyl, and thus well above the Windscale fire releases. The presence of the chimney scrubbers at Windscale was credited with maintaining partial containment and thus minimizing the radioactive content of the smoke that poured from the chimney during the fire. These scrubbers were installed at great expense on the insistence of John Cockcroft and were known as Cockcroft's Folly, until the 1957 fire. Health effects Of particular concern at the time was the radioactive isotope iodine-131, which has a half-life of only 8 days but is taken up by the human body and stored in the thyroid. As a result, consumption of iodine-131 often leads to cancer of the thyroid. Estimates of additional cancer cases and mortality resulting from the radiological release have varied. No one was evacuated from the surrounding area, but there was concern that milk might be dangerously contaminated. Milk from about 500 kilometers of nearby countryside was destroyed for about a month. A 2010 study of workers directly involved in the Klenupa Euro, and thus expected to have seen the highest exposure rates, found no significant long-term health effects from their involvement. Salvage operations. The reactor was unsalvageable. Where possible, the fuel rods were removed, and the reactor bioshield was sealed and left intact. Approximately 6,700 fire-damaged fuel elements and 1,700 fire-damaged isotope cartridges remain in the pile. The damaged reactor core was still slightly warm as a result of continuing nuclear reactions. Windscale Pile 2, though undamaged by the fire, was considered too unsafe for continued use. It was shut down shortly afterwards. No air-cooled reactors have been built since. The final removal of fuel from the damaged reactor was scheduled to begin in 2008 and continue for a further 4 years. Inspections showed that there had not been a graphite fire, and the damage to the graphite was localized, caused by severely overheated uranium fuel assemblies nearby. Board of Inquiry. The Board of Inquiry met under the chairmanship of Sir William Penney from 17 to October 25, 1957. Its report was submitted to the chairman of the United Kingdom Atomic Energy Authority and formed the basis of the government white paper submitted to Parliament in November 1957. The report itself was released at the Public Record Office in January 1988. In 1989 a revised transcript was released, following work to improve the transcription of the original recordings. Penney reported on October 26, 1957, 16 days after the fire was extinguished, and reached 4 conclusions. The primary cause of the accident had been the second nuclear heating on October 8, applied too soon and too rapidly. Steps taken to deal with the accident, once discovered, were prompt and efficient and displayed considerable devotion to duty on the part of all concerned. Measures taken to deal with the consequences of the accident were adequate, and there had been no immediate damage to health of any of the public or of the workers at Windscale. It was most unlikely that any harmful effects would develop. But the report was very critical of technical and organizational deficiencies. A more detailed technical assessment was needed, leading to organizational changes, clearer responsibilities for health and safety, and better definition of radiation dose limits. Those who had been directly involved in the events were heartened by Penney's conclusion that the steps taken had been prompt and efficient, and had displayed considerable devotion to duty. Some considered that the determination and courage shown by Thomas Tuohy, and the critical role he played in the aversion of complete disaster, had not been properly recognized. Tuohy died on March 12, 2008. He had never received any kind of public recognition for his decisive actions. The Board of Inquiry's report concluded officially that the fire had been caused by an error of judgment by the same people who then risked their lives to contain the blaze. It was later suggested by the grandson of Harold Macmillan, Prime Minister at the time of the fire, that the U.S. Congress might have vetoed plans of Macmillan and U.S. President Dwight Eisenhower for joint nuclear weapons development if they had known that it was due to reckless decisions by the UK government, and that Macmillan had covered up what really happened. Tuohy said of the officials who told the U.S. that his staff had caused the fire that they were a shower of bastards. The Windscale site was decontaminated and is still in use. Part of the site was later renamed Sellafield after being transferred to BNFL. The whole site is now owned by the Nuclear Decommissioning Authority. Comparison with other accidents, the release of radiation by the Windscale fire was greatly exceeded by the Chernobyl disaster in 1986, but the fire has been described as the worst reactor accident until 3 Mile Island in 1979. Epidemiological estimates put the number of additional cancers caused by the 3 Mile Island accident at not more than 1. Only Chernobyl produced immediate casualties. 3 Mile Island was a civilian reactor, and Chernobyl primarily so, both being used for electrical power production. In contrast, Windscale was for purely military purposes. The reactors at 3 Mile Island, unlike those at Windscale and Chernobyl, were in buildings designed to contain radioactive materials released by a reactor accident. Other military reactors have produced immediate, known casualties such as the 1961 incident at the SL-1 plant in Idaho which killed 3 operators, or the criticality accident which killed Louis Slotin at the Los Alamos National Laboratory in 1946. The accident at Windscale was also contemporary to the Kshtim disaster, a far more serious accident which happened on September 29, 1957 at the Mayak plant in the Soviet Union, when the failure of the cooling system for a tank storing tens of thousands of tons of dissolved nuclear waste resulted in a non-nuclear explosion. Irish Sea contamination. In 1968 a paper was submitted to Nature on the radioisotopes found in oysters from the Irish Sea. By using gamma spectroscopy, the oysters were found to contain 141 Se, 144 Se, 103 Ru, 106 Ru, 137 Cs, 95 Zr and 95 Nb. In addition, a zinc activation product was found. This is thought to be due to the corrosion of Magnox fuel cladding in cooling ponds. A number of harder-to-detect pure alpha and beta decaying radionuclides were also present, for example, SR90 and plutonium-239, but these do not show up in gamma spectroscopy as they do not generate any appreciable gamma rays when they decay. Television documentaries. In 1999, the BBC produced an educational documentary about the fire as a 30-minute episode of Disaster entitled The Windscale Fire. It subsequently was released on DVD. In 2007, the BBC produced another documentary about the accident entitled Windscale, Britain unregistered trademark's biggest nuclear disaster, which investigates the history of the first British nuclear facility and its role in the development of nuclear weapons. The documentary features interviews with key scientists and plant operators, such as Tom Tuohy, who was the deputy general manager of Windscale. The documentary suggests that the Windscale fire of 1957 the first fire in any nuclear facility was caused by the relaxation of safety measures, as a result of pressure from the British government to quickly produce fissile materials for nuclear weapons. Isotope cartridges. The following substances were placed inside metal cartridges and subjected to neutron irradiation to create radioisotopes. Both the target material and some of the product isotopes are listed below. Of these, the polonium-210 release made the most significant contribution to the collective dose on the general population. Lithium-magnesium alloy, tritium, aluminium nitride, carbon-14, potassium chloride, chlorine-36, cobalt, cobalt-60, thulium, thulium-170, thallium, thallium-204, bismuth oxide, polonium-210, thorium, uranium-233. See also: Nuclear and radiation accidents, nuclear meltdown. References. Further reading: Weckeford, R. The Windscale Reactor Accident, 50 Years On. Journal of Radiological Protection 27, 211 5 doi, 10.108827E02. Windscale fallout blew right across Europe. Rob Edwards. New Scientist, October 6, 2007. Windscale, 1957, Anatomy of a Nuclear Accident, Lorna Arnold. New York, St. Martin's Press 1992, Chernobyl, Worst but Not First, Walter C. Patterson. Bulletin of the Atomic Scientists, August-September 1986. Secrets of the Windscale Fire Revealed, F. Pierce. New Scientist Vol 99 September 29, 1983 pages 911, Windscale. Increased cancer incidence alleged, T. Beardsley. Nature Vol 306 issue November 3, 5938 1983 pages 5, Accident at Windscale No. 1 pile on October 10, 1957. CMND 302, Accident at Windscale, World's First Atomic Alarm, Hartley Howe. Popular Science, October 1958, Volume 173, No. 4. An Assessment of the Radiological Impact of the Windscale Reactor Fire, M. J. Crick, G. S. Lindsley. NRPB Reports, October 1957, November 1982. An Airborne Radiometric Survey of the Windscale Area, October 19 to 22, 1957. AERE Reports, No. R2890, The Deposition of Strontium-89 and Strontium-90 on Agricultural Land and Their Entry into Milk After the Reactor Accident at Windscale in October, 1957. AHSB, Accident at Windscale. British Medical Journal, November 16, 1957. 2 pages 1166-8. External links, Windscale. Nuclear Decommissioning Authority. The 1957 Windscale fire, lakestate.co.uk. July 5, 2009. Windscale nuclear incident. The Virtual Nuclear Tourist, December 22, 2005. 1957, inquiry publishes cause of nuclear fire. BBC. November 8, 1957. Marston, B.J. Preston, South Dakota. Wickham, A.J. Tyson, A. Evaluation of graphite safety issues for the British production piles at Windscale. IAEA. Paul Dodgson. Radio plays, Energy Industry, Windscale, 2007. suttonelms.org.uk